Hi, today we're going to learn about Pascal's principle and the continuity equation. We'll start with Pascal's principle. Pascal's principle basically says that any change in the applied pressure on an enclosed fluid system is going to be transmitted undiminished to all parts of that system. So, in other words, if I have, let's just look what I have here. I have a 1 kilogram piston, let's say, that has an area of 1 square meter, and it's applying an mg of 10 newtons across 1 square meter. So that gives me 10 pascals of pressure caused by this. If I was then to add a 2 kilogram mass on top of it, I would be changing the pressure of the system. There's now 30 newtons acting on 1 square meter. So I went from 10 to 30 pascals, and that pressure will be exerted on all parts of this fluid system. So everywhere in here is going to experience that same change in pressure. So what it tells me is you can't have different pressures in one part versus the other because it's a static system. Usually, when we see examples of Pascal's principle, what we have is two cylinders of dissimilar area. Usually, you have a big one and a smaller one, and they're connected by some sort of a tube so that the pressure can be transmitted throughout this whole fluid system, this enclosed fluid system. And so, what Pascal's principle tells me is that the pressure here, 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 and the pressure here all have to be the same at all times. In other words, P1 is always going to equal P2. Regardless of changes in area, the pressure has to be the same. Now, pressure, if you recall, is force over area. So F over A here is equal to F over A here. So what I find is if the area gets bigger, the force has to get bigger in order to make sure that the pressure here is equal to the pressure here. Let's take a look at an example. Okay, so let's just say that I have a piston here. In this case, we're going to say our pistons are massless. If I apply a 2 kilograms here, that's 20 newtons is applied to 1 square meter. So that means I have 20 newtons of pressure exerted on this piston. That means there's 20 pascals of pressure throughout this system. So if I come over here, I have 2 square meters. So if I was going to balance this and keep the system from moving, I'd have to put 4 kilograms here because 40 divided by 2 is equal to 20 divided by 1. So this is a kind of an interesting thing. I apply a small force to a small area, and I exert a large force across a large area. That's basically what this tells me. So this is used a lot in industry. Okay, we call this hydraulic presses or hydraulic brakes or hydraulic. When we see the terms hydraulics, basically means we're taking advantage of Pascal's principle. So take a look at this example here. I have a 1,200 kilogram car sitting on a large cylinder, and over here I have a small cylinder. So I'm going to call this A has an area of 0.25 square meters and B has an area of 4 square meters. It wouldn't be enough to lift a car, but don't worry about that. Okay. So the question is, how much force would be needed to apply to the small piston in order to lift the 1,200 kilogram car? So I'm just going to say F1 over A1 equals F2 over A2. I know that F2 is equal to the mg of the car. And I want to figure out what this force is. So force over 0.25 square meters is equal to mg over 4 square meters. And when I solve for F, I get 750. So what that means is I push down here with 750 newtons, and I lift here with 12,000 newtons. And that's because this area is so much smaller than that area. It's basically 16 times smaller than that area, so it applies 16 times more force. Now, you can also think of this in terms of conservation of mass. Okay, so if you think about this, so let's just say I have a cylinder here that has a cross-sectional area of 1 square meter, and over here it has a cross-sectional area of 2 square meters, or total area of 2 square meters. Okay, so the idea is if I push down 2 meters, how much volume of fluid have I moved? Well, I've moved 2 times 1 meter squared. So that's 2 cubic meters of fluid were pushed into here. So if I add 2 cubic meters over here, well, 2 meters squared times 1 meter, that tells me this is going to go up half as much as this one went down. So when this area is half as big, it's going to go down twice as much. This one has twice the area, goes up half as much. Now, This has interesting implications in terms of conservation of energy because remember, work equals force times distance. And so what we find here is since I can't, this, clearly this isn't a system that's going to like generate energy. It's simply transmitting force. So the work in equals the work out. We're ignoring any kind of internal friction here. So if I apply a force of 20 newtons, we say, well, 20 newtons times 2 meters is going to equal 40 newtons times 1. And we see that that's actually the case, that this, I would end up doing 40 joules here of work in would give me 40 joules worth of work out. So that's Pascal's principle. It's really straightforward. You just really have to remember F1 over A1 equals F2 over A2. Now, the continuity equation is actually a bigger deal, and it has a lot of ramifications for the next subject we're going to study, which is called Bernoulli's principle. So here's what the continuity equation tells us. In an incompressible fluid, the total amount of matter in here can't change. So this is really about, again, about conservation of mass, which is really what Pascal's principle was as well. So if I was to move 6 cubic meters of water into this side of this tube, this pipe, then I have to move 6 cubic meters of water out because I can't have since it's incompressible, I can't change the total amount of water that's in here. It's a fixed amount. So really what it's saying is the volume that goes into a system has to equal the volume that comes out. Pretty straightforward, but let's see what some of the implications are because they're pretty cool. All right, in order to see why it's cool, you have to understand a concept called flow rate. Flow rate, if you think about it, just like how many cubic meters per second flows through this system, okay? So often we say like pass a given point in the system, but just basically what is the rate of volume in versus volume out, okay? So let's just say then that it takes 2 seconds to move this into here. Well, then my flow rate would be 6 cubic meters per 2 seconds, or in other words, my flow rate is 3 cubic meters per second. Every second, 3 cubic meters of material is going to move into and therefore out of this system, or past any given point in here. In 1 second, 3 cubic meters will go by. All right, now let's see why this is kind of cool. So think about this. Flow rate, remember, is cubic meters per second. Well, if I have a cross-sectional area, which is in square meters times meters, equals volume. So it turns out that flow rate can also be expressed in terms of area times velocity. Let's see why. Flow rate, again, is cubic meters per second. Area is in cubic meters, so if I is in square meters. So if I say square meters times meters per second of fluid velocity, what that gives me is cubic meters per second. So let's just look at this case here. I have a pipe with a cross-sectional area of 2 square meters, and I have a fluid flowing through it at a velocity of 4 meters per second. So what is the flow rate in cubic meters per second? Well, I would just say, well, I have 2 square meters of area times 4 meters every second. So that's going to give me 8 cubic meters per second of water going into one end of the pipe and out the other end of the pipe. Now, if we look at this diagram above, and this is what they're usually going to show you, is you have a system where I'm going to change the diameter of the pipe. I'm usually going to have it get either wider or narrower, in this case, narrower. So here I have on this end, the opening here is 6 square meters, but it's going to move into an area where it narrows down to 1 square meter. I think you can see, well, if the flow rate stays constant, the velocity's got to change by a factor of 6. So let's just see what happens. Here the water comes in at 1 meter per second. So what is the flow rate? Well, the flow rate is going to be 6 square meters times 1 meter per second. That gives me 6 cubic meters per second of water of fluid moving into here. So I had to have 6 cubic meters coming out of it every second. So over here, I'm going to say, well, area here is going to be 1. I know that the flow rate is 6, so that tells me the velocity has to be 6 meters per second in order for it to equal 6 cubic meters per second. So what we find it is, however much the area shrinks is how much the velocity increases. So if this had an area that was 10 times smaller than this, the velocity here would have to be 10 times greater. If things are flowing this way, the area got 2 times bigger, then it's going to have to flow 2 times slower. All right, so you just had to keep in mind that it's just area times volume equals area times volume. So we call this the continuity equation. We just write it this way. We say A1, that's the area of this part of the system, times the velocity here, not the flow rate, but the velocity, is equal to the area here times the velocity here. And that's because the flow rate has to equal the flow rate, because I can't build up any fluid in there. It's always got to be constant. So let's look at a couple examples. I try my best to draw a little syringe, like you'd have for squirting water, okay? Or like a doctor giving you a shot, but we'll say it was for squirting water. So the idea is the plunger of the syringe, this is supposed to be where you hold your fingers, and here's where you push with your thumb. I thought I did okay with my diagram. Okay, so anyway, the plunger has area A, and the outlet has area 1/16 A. But it's not really rocket science. So you can see if however much this gets smaller, is how much faster the velocity has to be. So let's just say then that I'm going to compress this distance d in times t. Well, distance divided by velocity is distance divided by time is velocity or speed. All right, so this is the velocity of fluid. So remember, a times v equals a times v. And here I know this is 1/16a, so the velocity here has to be 16 times the velocity here. Basically, since this is 16 times smaller, the velocity has to be 16 times greater. Now, this one's kind of cool. If you've ever watched water come out of a pipe, you notice it gets skinnier as it comes down, right? I'm sure you've noticed it. And if it gets skinny enough, it just breaks in little droplets when the what do you call it? The cohesive forces everywhere you call it in the water overcome that. So here's what you got then. So let's just say I have a pipe that has a cross-sectional area of 20 square centimeters, and water is exiting out of the pipe at 4 meters per second. Not a flow rate, but I'm giving you a velocity here. Okay. What I want to know is uh, if water exits this in a vertical direction, and uh, I want to know what is the cross-sectional area of the stream after it's fallen a distance of 2 meters. Now, this is a continuity equation. So I had to say A1V1, which I have here, is equal to A2V2. And what I want to know what A2 is, so I got to figure out what V2 is. I'm going to have to use kinematics. So this is how I'm going to solve it. But in order to do that, I've got to figure out how fast is this going to be going after it's fallen 2 meters. Now, what I don't know is the time. So this is the equation I'm going to use. I'm going to say, well, the final velocity squared is equal to the initial velocity squared times 2g and delta x. So I'm going to say, well, it came out at 4. So 4 squared plus 2 times g, which is 10, times 2 meters 2. And when I solve for this, I'm going to get 7.5 meters per second. So it came out at 4, and 2 meters later, it's going 7.5. So it's almost doubled its speed. So therefore, I would expect the area to be about half of what it was. Let's just see what we get. So we're going to say A1V1 equals A2V2. So A1 was 20 and V was 4. I don't know what A2 is, but V2 was 7.5. And when I solve for A, I get 10.6. It was 20, and it's almost 10 now. So it went down by almost a half, as we would have expected. Now, one last thing. This does sometimes come up, so this is a little bit tricky. Sometimes we have systems where it branches. Okay, now so don't freak out. It's really not that hard. When that happens, I'm just going to take the continuity equation. I'm just going to put in for number of branches in front of it. Okay, so in, which means how many tubes I have over here, N1 times A1 times V1 is going to equal however many branches. In this case, 3. That's in out, A out, V out. And I could do this as, so anyway, so let's just try this here. So in this number of branches. So here's what we get then. Okay. So if this cross section of the area is 4 square meters and the speed is 3, each of these has an area of 1. What is the speed of the water flowing through these pipes? So I just say, well, I have one pipe here. So N is 1. It's got an area of 4 and it's traveling at 3 meters per second. Now here, N is 3, the area is 1, and I want to solve for the V, and when I solve for it, I get 4. Okay, so that's Pascal and continuity equation. It wasn't that bad, was it? Okay, thanks for watching.